This is just maybe something that's emerging in quantum matter, soft matter, and living matter that unites us, or maybe we'll see that it divides us. I'll find out soon enough, depending upon the response to this. But famously in the 1960s, there was a movie called The Graduate, where at the beginning of the movie, the character, who was a recent college graduate, was told by an older person, I just want to say one word to you: plastics. And so, okay, two words: machine learning. Machine learning is entering, whether we like it or not, machine learning is definitely entering quantum matter, soft matter, living matter, and materials for energy, and all in big exponential ways. This is a chart from correlated matter showing sort of an exponential ramp up of machine learning papers. This is a plot from soft matter showing an exponential ramp up of machine learning papers. This is machine learning in batteries right here. And some of you may know a former Davis student, Austin Sindek, who was named one of the Forbes top 100 for his work in this area here. This is machine learning in catalysts right here. Some of it is very practical minded, but it's not just data driven. This is a paper where machine learning is actually being used to design variational states to describe neural networks, quantum states of matter, many body quantum states of matter. And this is something that I know David Schwab at the City College of New York is working on. Ab initio solution of many electron Schrodinger equations using neural network designs to actually learn the possible sort of quantum connections of those states. And then this is a paper that was quite lovely from the collaboration of Zhang, Melko, and Kim, which is using machine learning to identify quantum spin liquids in model Hamiltonians. And they use machine learning to actually identify this phase boundary between a topological phase and a disordered phase in the space of these coupling constants here. And it's also data-driven and practical. Machine learning with a lot of data from experiment and from quantum calculations can actually do a better job than the systematic error from hybrid density functional theory, for example, in materials applications. It can be used to learn fast charging protocols for batteries, which for those of you like me who have an electric car is of some interest. So we can both safely charge them and keep them from exploding, and also just charge them quickly. This is where Jose might, hit me over the head or something, but I'll go ahead and put it out there and see what people think. So this is the protein folding problem and protein-protein interactions. And nobody is more of an expert on that than my co-chair, Jose Onashik. As you know, this has been one of the successes of biological physics, how do we understand how we can go from the sequence of a protein to a folded structure in seconds versus universe lifetimes. And something that Jose has also worked on is how can we actually go from data to the structures of complexes for protein-protein interactions. And I don't know if Peter's still here, but Jose and Peter, of course, have done fabulous work over the years on understanding how we can get folding funnels from minimal frustration principles in the evolutionary design of sequences for proteins. There have been amazing advances in the direct simulation for relatively small proteins. So for example, David Shaw's group, you can actually see small proteins fold directly on the computer given a sequence. And Jose and Terry Hua and others have worked on the direct interaction method, where you look at co-evolving mutations to identify interactions between complexes and use that to predict structure. But you can also kind of, let's see, something happened here. I'm frozen, apparently. Oh, I'm frozen, apparently. Oh, here we go. You can also surrender to the machines. So, AlphaFold has, and RosettaFold from David Baker's lab, AlphaFold from the DeepMind, have been released. Their codes have been released to the public in the summer of 2021, and there's been an explosion of publications resulting from this, with the assistance also of a user-friendly Python notebook interface called ColabFold that can be used on the Google Colab space. And AlphaFold can be used to predict the structure of proteins as well as the structure of complexes directly from, I think I missed something here. So this is the structure of, the folded structures of these proteins are predicted very accurately by providing the sequence to AlphaFold, which then has used structural data to essentially learn the principles of protein folding without sort of the intellect going into the discovery process and the learning process rather than going into sort of extracting those physical principles ahead of time, those emergent principles ahead of time. And AlphaFold has also been destroying the competition on the CASP competition, where you predict structure from sequence, where you don't know for sure what the structure is, and you predict the structure and then compare it to an experimental sequence. AlphaFold comes from Google DeepMind. RosettaFold comes from the Protein Design Institute of the Baker Lab at the University of Washington. And I just wanted to, these are these papers which are exploding, but also AlphaFold and CoLabFold can be used to predict the structure of complexes. These are some successes where these heteromers and these complexes were actually predicted from the deep learning algorithm of AlphaFold multimer. This is one that didn't do as well. It sort of got this part right, but it didn't do very well on this part. But you can use this for new science. And we actually, I don't want to be too boastful, but we're proud of this. We did actually predict the structure of a small sequence from the spike protein of SARS-CoV-2 and how it binds to the furin protein. The yellow and red here are the furin protein. The red is the actual structure. The yellow is the prediction from AlphaFold. And then this is the binding region from the spike domain of the SARS-CoV-2, which has not been identified structurally. So we made a prediction about where that binds. When we explore the ramifications of that prediction, we predict that the Delta variant actually binds stronger than any of the other variants or pretty much any other virus out there. And that, in fact, there's probably an upper bound to the binding strength, which happens to be right at where the Delta residue is. If you look at the number of positively charged amino acids on that sequence of amino acids that binds to the furin protein. What that's important for is that the furin protein is what drives a lot of the bad behavior of the Delta variant. And so if, in fact, Delta is as bad as it gets, that's actually useful information to know. So the question is machine learning a new tool of science that will help us, like R2-D2 over there, or is it pardon the puns, the termination of traditional science? So I guess that's just to be provocative. I'll leave that out there.
Okay, thank you, Daniel. I think it's a good start for that discussion. I think there is lots of interesting points you brought up, and I think there was the points that Evelyn brought up. And what I'm curious to hear from people is just to put a little bit of history on here and sort of be provocative with peers and Dan Koch is also that have been ahead of ICAM for such a long time, basically, particularly Dan, and that made the transition from Dave Pines. When Dave Pines started ICAM, he had this idea of complex systems, but also he said, let's focus on complex systems that I'm interested in. And okay. So in a sense, we started and I think that's what we come in a full loop. We started with two communities that sort of, we were all friends, but we're interested on very, very different problems. You could break the people, the H bar equals 0 people versus the people that are really quantum, and appears to be two things very different. So what we're bringing to this discussion now is if there are some principles in complexity that actually are robust enough that can go across many, many different processes. And I think Evelyn made her case on these edge states that basically appear to be stable, robust solutions for problems very, very different, basically, from topological insulators to the case of biological cycles. And what I'm trying to add here, and add a question to everybody, is appears that you can go to cycles and using the idea of edge states, particularly this reduction of dimensions, right? Basically, in order to fall into the system, both of the system, there's a tremendous reduction of dimension. We start with a system that are complex in dimensions. Is this a phenomenon that affects are these phenomena something that is a good solution, or there's actually, I would expect that most of the oscillators in biology fall into that category. So I think it is basically, it's always a question in terms of asking is, do I have a method in search of a solution, or do I have a solution that's actually universal? And basically, just to put the discussion for this group here, and the people that are used to ICAM on the old days, remember the paper, Peter is not here now, but the middle way, do we have these proctorates? That's something that Pines used to love about it.
Yeah.
Right. So basically, can we get these ideas and inform the class and see the different problems fall into that category? So I just want to open the discussion based on that.
Well, first of all, even in the case that Daniel was presenting, the machine learning, a lot of the ideas for machine learning have come out of studying very simple systems. So spin glasses were systems with many valley solutions have been models for developing these kinds of approaches. And so I guess at some level, even if DeepMind or AlphaFold won't share with us the secrets of protein folding, the methodologies of physics of looking at simple models provide us with a route that got us to those kind of algorithms. Important to realize that. But I guess my question would be whether continuing from what Daniel said, is it important that we learn the principles that govern protein folding so that we can go to the next level, or are we content to just let the machines do their work and just marvel at the quality of the solution?
Okay, so let me add something to that, because that's something actually interests us for a long time. I think the idea, basically, if we are getting the current AlphaFold and situation like that, they happen because protein folding has these funnel landscapes and are minimally frustrated. So if you didn't have this universality class, the system being minimally frustrated, you will have this relationship that comes between, for example, in our case, what we come to covariance that Daniel was saying, we can go to information from sequence and figure out that basically coevolution, basically commutations are actually we can identify structure from the fact that these things have to evolve to give this minimally frustrated landscape. So one of the things that you have on AlphaFold is that basically when we started with Terry Hua and Martin Waits, and then now Farouk Morkus in my group, we did a little bit of that work, but AlphaFold actually curate a database in coevolution that cost them a fortune. So in a sense, basically, they haven't done new physics. They actually got the physics that they say that the original paper, and they actually applied the engineering of machine learning using these ideas to a deeper level, based by having a lot of more sequence information that you had. They spent almost $4 million curating this database that actually helped them a long way. So in protein folding, we feel very good that I think many years ago, we already knew what was the general mechanism of protein folding. But now you can use that mechanism together with machine learning and go to sequence space and do very, very well. What makes AlphaFold especially good, what makes the difference is that predictions are already good before that, but they're coming to the level that they can compare crystallography at the level of the phase space, right? So they're going to that level that basically is almost to the point that you say, do I believe more the AlphaFold result or do I believe crystallography? We are getting to the error about the same level, at least for small proteins, not for large proteins, right? That Daniel was talking about larger systems. The game changed a lot. They are much more dynamical, but at least for small systems. So I think that's a very interesting question, because in many of the systems, if you have some physics understanding and you believe that you have some clear class of problem that falls into a category, like the case what we call minimal frustration, funnels, and stuff, then you can actually do a lot of machine learning the top of it, but you don't do something like completely out of ignorance. In a sense, you're trying to get information into that case, basically, And I think that's the point that I want to point out here. When you have, by having a physical understanding, if I believe you fall in a class of, if I fall in the class, like if I go back to now what Evelyn was saying, that you have these edge states. Can we start now assuming that's the landscape you're dealing with? Can now I start to learn the parameters from data and go in there? And you saw some other physical things where people are trying to get the entire phase space of the situation, but it's also assuming that fall into a certain class of models. So so the first thing is, do we know those models? Do we believe on that? And also, are they transferable from very different problems? And that I think the point of that discussion. The edge states are basically that they can help solve problems in a complete different variety of a system. Basically, here where we discussed the discussion about topological insulators and biological oscillators.
And just to add on that, I mean, I think that the kinds of applications that it was actually a DeepMind paper that was looking at the quantum have many electron states of molecules and so on as well. It's quite possible that just what you're saying, Jose, that there's some kind of a protectorate for the sort of network topology that's relevant for linking the many body states together, and that's why it might work. That it's not just anything is possible, that there might be a fairly restricted subset of things which are preferred, and that's why it works in identifying those states effectively. And that's, I know in the work that David Schwab is doing, that's the kind of thing that seems to be emerging from his picture as to why deep networks work, is that they sort of where they work well is they work well sort of when you're close to some critical structures. They could presumably have some protectorate associated with them. So I think that's an interesting line of thinking about this.
So just to add to what Daniel is saying, and in terms of these proctor rates, I think I love to bring that discussion, because if you think about it, that's a word that appears on the ICAM discussion 20 years ago. And I think it's very pertinent what's happening in science now. So I think historically it would be a very interesting thing that to say it's a concept that's ICAM developed concept that's now is evolving. So I think it's interesting for this community. But one thing people are learning on these days with machine learning is that we're always worried about overfitting and getting wrong answers. And actually, we have been much more successful. People have been finding local minima into this process that actually are reasonably good answers. That's something Hopfield used to discuss a long time ago when you're discussing basic NP-complete problems and find polynomial solutions. So the question is, why these local minima are good solutions? In protein fold, you understand that if you have a funnel landscape, if you're always going to funnel down, you may do some minor mistakes at the bottom of it, but you're going to end up with things that are not completely similar what you're looking at in that particular. So that's where minimal frustration funnels became very important. But this phenomenon also true for other problems in machine learning, because actually what people are noticing is that the solutions that basically these different local minima are actually reasonable solutions for the engineering problems that people have interested on. So that's an interesting question. It goes again, what we talk about Dave Schwab that you're talking about. That's basically how these things work. And in a sense is basically the questions people believe: do we have enough data? Don't we have enough data? How do we learn? How I know if we're overfitting? And actually you're doing better than we expected. And the mathematicians there's a lot of mathematics being done on that, that's sort of trying to show about this sort of this landscape of solutions. That's an interesting question for this group.
Hmm.
So we have a lot of other people in here working on many different problems in both interface. Do you want anybody else want to comment on that here? We have a lot of people that may want to say. Who was on the list, Daniel? You had the list of people here. I have to go.
Well, let's see. I don't. Some of the people that were on the list.
Let's try to put people on the spot here, Daniel. Well, let's go. Go for it.
Well, in order to prevent you from doing that forcefully, let me volunteer.
All right,
So
Andrew, go ahead.
this is Andrei Nevedomsky from Rice. So one of the questions that comes to my mind when I look at the use of the machine learning is the question of not so much reproducibility, but whether there is any deep underlying scheme that makes it work. And as you pointed out, Jose, in the case of protein folding, there's this funnel landscape that you and Peter Walnes discovered, and so there is some understanding for why it might work. Now, my understanding is that mathematicians often, try to explain or find certain mathematical models, trying to explain deeply for why deep neural networks work. And my understanding that it's still an open problem. So I'd like to bring it back to Pierce's question. Should we be satisfied with the fact that it works empirically and is applicable to some problems? Should we try to find mathematical reasons for why it does work? Should we try to look for counterexamples, or should we just reject the whole thing saying, well, it has a limited usefulness?
I think anyway, what brings us together is we're all interested in using models as, I heard the word motif in Evelyn's talk, as examples that we can learn to characterize much more complex cases that we come into contact with. And so one of the things that certainly brings us all together is a common interest in models. And presumably in training students, we need to keep working on it. This is how they learn. And part of the question that we posed here is partly because presumably there is a commonality of learning and education that we need for our students, so that they will be able to span this very broad area of complex phenomena, from understanding quantum gravity, strange metals, out to understanding complex dynamics and complex structures. And so it's an important issue to understand what brings us together, because that will determine the kinds of groups, kinds of curricula that we design in the future for incoming students that will help these fields advance. I mean, one of the questions is whether we can just hand it over to the computer scientists. They just take all the data, feed it into the machine learning, and out will come the answer. But of course, that is indeed the beginning of the end, I would imagine, for science, as Daniel said. But my guess is that you need principles to guide your understanding of these complex solutions, and you can use them as a tool to get to the next level. But I don't know.
I would like to raise the idea that machine learning may have some bearing on an issue which has intrigued me for a long time, and that's the interplay or the relationship between reductionism and emergence. I think Phil Anderson, in his article about more is different, played around with this just a little bit. The article seemed to say that you can do reductionist science, but you may not be able to go the other direction. And then in a parenthetical remark, he seemed to kind of take it back and say, of course, I'm not telling you can't do reductionism, but you could pose it like this. If I tell you the Hamiltonian or all interactions you need to know about the various constituents of the system, can you just predict everything that will happen from that? Can you always go backwards? And or not? Could it actually be the case that you can't predict the emergent behavior, even if I give you the biggest computer and all that? And it seemed to me that for a long time you could say, well, we really don't know because we don't have computers big enough. But the machine learning is beginning to be able to ask whether a Hamiltonian could support this or that topological state, which you might not have been able to do before. So So are we now to the point where we're just going to say, okay, the reductionists have it, and you just tell them the basic stuff and they can tell you everything that's going to happen? Or is this even an interesting issue still or not? Or maybe it's just the result of me being not very bright and not catching it all.
That's a very, very good point. And let me just to try to sort of make a little bit more concrete that statement, okay? I think one thing that came from Evelyn talk and came from talks before is this reduction of dimension, the dimensionality of the problem in problems where you have a bias that can help you to find that. If I had a complete random landscape, or if you want, a blind person on a flat golf course, then problems like that doesn't help you. Machine learning won't help you because they provide no information whatsoever. So if these are the problems you're dealing with it, right? If you have the blind person on a flat golf course, until you find the hole, you have just any information you have is completely irrelevant to help you to find the minimum of that problem, right? So in any problem we have, basically that we discussed today, there's some way that we can reduce the complexity of the problem to a smaller dimension, and then somehow we can learn from data. So I think all these things come together. And the question is, are the problems you're interested in falling on that class? And I think Daniel was trying to make that case before. And I think just the fact you're trying to plot something in 2 dimensions and say, here are the different phases I'm looking at, it tells you that you have this ability, at least some base, you know the coordinates you're looking at, that if you had a complete random landscape or a flat landscape, wouldn't help you.
So that maybe the problems that we're interested in studying, which have robust discoverable phenomena, tend to fall into a category where there is some kind of a protectorate, a minimum.
Exactly.
Of
That's where the protectorate came from ICAM, and the question
right.
is,
it's like an extremum, minimum, and an appropriate objective or cost function, if you will, and that's certainly a language that is shared with neuroscience and computer science. I don't want to, I maybe risk it by putting Randy on the spot, but I see that Randy's here. I don't know if Randy is willing to step in and say anything, but Randy's actually a neuroscientist and a computer scientist. So I don't know if you want to step in and say anything.
Rajiv has a question or a point first.
Okay.
I was just going to say that perhaps machine learning has just passed a certain threshold so that some new problems have opened up that can be addressed using computers and just raw computing power and data. But that doesn't mean that all problems have been solved. I mean, complexity is a ever larger and larger, it has many, many aspects to it. And I'm sure there are lots of other problems which will require new thinking and, the kind of Andersonian thinking that that we basically believe in. And I don't think machine learning is going to replace that entirely. But anyway.
Well, just jumping in here, I am obviously new to this kind of whole community, but from my perspective, machine learning as it's traditionally practiced, is largely function approximation, right? And so there's been traditional ways of doing low dimensional kind of function approximation, and this is just a way that we can do efficient high dimension function approximation, but it really isn't anything more than that at some level. So it doesn't give you the answers, it just basically fits the existing data that you have. It tries to allow you to extrapolate and interpolate, and the ability to discover those regularities in the functional mapping between 2 variables, whatever, that obviously is extremely powerful, but in and of itself, it isn't magic, in my opinion. So that's just one thought about that. The other idea overall is that the Hopfield network, which I guess has currency here, is very much at the heart of the models I'm working on for understanding the brain. And there's a big question about the relationship between kind of machine learning approaches and what's going on actually in the brain. This is actually what I'm going to talk about tomorrow, so I won't say too much here, but I do think none of the existing models are relying on anything at all connected to the Hopfield models. There are essentially no interesting dynamics in these machine learning models because dynamics are complex, right? Especially if you get away from a fully symmetric connectivity matrix, which gives you the attractor states that are characteristic of the Hopfield network. These states go off into chaos, right? And I do think that characterizes that the brain is characterized by something that's approximately symmetric, but not entirely. And so, that whole space of what's going on in the brain and really understanding kind of the dynamic picture of the brain is, I think, not very well covered by existing machine learning models and is still very much a frontier. So I think there's still a lot to be done there that probably the tools that you guys use is very relevant. And not, there's a lot of real problems that haven't been solved yet. Let's put it that way.
I had never thought of these approaches, but just hearing you at this level, I don't see how machine learning would have discovered the double helix or even the pairing in superconducting state. I don't see how machine learning would have been able to discover these kind of things. My feeling is that machine learning is an optimization tool which might be used once we have very good principles that we have understood by working, by doing science the way we do it. So, for instance, maybe machine learning will find the room temperature superconductor. I don't know, but I am not even sure of that because maybe the room temperature superconductor will need a kind of pairing that we didn't think about at this stage. So I am a little bit scared of this approach. Being an experimentalist, I know that that the experiments are you learn by finding things that you do not expect at all. So I'm not sure that the machine will find these things. Okay,
that's good.
It's
Do you have something else to say? I'm sorry, continue. Please.
It's just a prejudice that I have being coming from the experimental side. I am afraid, well, there have been at the beginning of the high TC business, people have tried to do the equivalent of machine learning has been to build a machine which are mixing all chemical elements, trying to do to build all the perovskites possible, and they never found a new superconductor. So okay.
I think that does.
I didn't think that enough about that.
So I'm just add one comment. I completely agree with you here, and I think I'm more on your field than other people's field. I think there are problems, like in the case of protein folding. 10 years ago, we said when people have enough data, when people have enough information, because of the landscape, because we understand the basic principles, things are going to work. And so for me, it's not a surprise that's working. It's great engineering, but you have a modeling before. The trouble we have now is there are people on the other end, and I think Daniel did a good, very provocative introduction, where say we can get problems that we know nothing about it, and we may learn by just creating some crazy network here. And basically, that's where Randy put a big word of caution. I'm glad he did it. And we are just going to learn some basic principles by just look at the data, right? So basically, and we can go to your expression, right? Basically, right? We can just looking at things, we can see a lot. And basically, so I think it's an interesting question. I have my doubts about that, but that goes back into the idea of what we were discussing of proctorates. If some problems for some of these proctorates, we may be able to learn something, and which are these proctorates that came out. I think protein fold is one of them, clearly. Are these sort of the states that basically in Evelyn's talk, that basically going from topological insulators to oscillators, they create another class of proctorates. That's a very interesting question. I think that Andre is trying to say something, right? He has his hands up.
Yes, well, I didn't mean in any way to interrupt.
No, please go ahead.
Yeah, good.
I was gonna, let's see. I was gonna comment on Henri's comment, but also ask a question to Randy. So see if I can make it all in one go. So maybe some of you have heard about generative adversarial networks. If you do not, look at the website thispersondoesnotexist.com. It's an example of using neural networks not to not the reductionism as you know, one of the examples, but rather to try to generate something based on ICAM principles or prior examples, right? And I guess the question I wanted to ask Randy is, because I just don't know enough about this. In order for this GAN generative adversarial networks to work, do you need millions and millions of examples? Could one instead give you, I don't know, of the order of a couple of dozen examples of chemical compounds that you want and say, look, here's a periodic table. Let's say we're only looking for tertiary compounds, so that the phase space is large, but it's not unlimited, right? We have way more facial features than the chemical elements if you only limit yourself to tertiary compounds. And then you ask, okay, well, can I try and predict, just like I can predict a woman's face, can I predict a compound that would be a high DC superconductor? So what is that even realistic? And if yes, do I just need to have a lot of supervised learning and therefore lots of database entries? Is it as simple as that, Randy?
Yeah, and so I think that's a great example, because the magic of the GAN is a formula for creating much more data than you actually originally start with, and that's the kind of generative aspect of it. This goes back to this point that all of these techniques are function approximators, and they're only as good as the data sampling you have, right? So if you can densely sample some function, you can approximate it using these techniques. But if you don't have much data, you can't do a very good job, right? And so the real tricks that are going on with the GAN, and also a lot of the work that DeepMind has been doing with like the agents that learn to play chess and Go, et cetera, all of that is ways of basically having agents playing against each other to create more and more data, right? And so a lot of these techniques are essentially clever ways of amplifying the amount of data that you have, so that the system can do a much better job of learning. And so with the GAN, you basically have these two systems kind of mutually training each other. And it's very, very much like the two agents in the kind of game of chess, each one playing against each other, and they can kind of basically, each improve, and you kind of do this generational thing where, as one gets better, then the other one has to get better to win, et cetera. And so you just have this way of kind of amplifying the amount of learning that's going on.
I see. So in my example of the periodic table, I mean, is it possible? I mean, what would you need? Would you need somebody to tell you at each instance whether you're winning, like an equivalent of whether you have a checkmate or not? You have to tell was the superconductivity C is higher than 40 Kelvin or less?
Yeah, but you need a simulator there, Andre.
Yeah.
That could simulate real chemical behavior, right? And we don't have that simulator, so you'd have to have Henri in the back room making the compounds and doing the measurements to provide the data.
But that's my question. You see, I don't think GAN does that.
It has a so one of the two systems, right, is sort of essentially the adversary, the critic, right? And one is the generator, right? And the adversary doesn't actually have all of the ground truth. and it's kind of guessing as well. And so, you know, the generator comes up with a potential, like in the case of faces, it comes up with a face. The adversary, the critic, says, that doesn't look like a real face. Try again. That trains the generator to come up with a new example. But the adversary initially accepts, the critic, initially accepts very bad faces. So it initially says something that looks anything at all like a face is like, yeah, that's good enough. And then it's learning too to become better and better at a critic. And so it is this way of kind of each side is actually learning, and each one is kind of upping their game as they go along. So the ultimate kind of ground truth of like the periodic table could still be there. The problem with that is like just the dimensionality of it is very small. So like, I don't know what you would do with that, but if you had all these kind of compounds or something that you were creating out of elements, and you did have certain amount of ground truth, it could potentially, the adversary could sort of, you know, guess some factors about whether this was a, you know, whatever properties of these chemicals you're trying to estimate. It could potentially work. Anyway, so it's like it is a way of magnifying a small amount of data to really get the most mileage out of it. So it is I think a very profitable potential way in which these systems could work. And I don't know if like the DeepMind AlphaFold is using that technique at all, or they have other ways of getting around this problem.
But that is an optimization problem. You have to put at the input something which is realistic and which is going to drive the phenomena that happens. If you have that in hand, I think that playing with computers will help to go faster than you would be by yourself. But you have to put the right input. I mean, somewhere you have to pair the electrons to do a superconductor. So if you don't know that, you are not going, let's assume you don't know that there is a pairing. If you don't know it, I'm not sure you will find it.
So just for completeness, since Rand was asking, AlphaFold just used the idea of covariance. That's something we showed a long time ago. That basically, that if you have many sequences that fold into the same structure, you can look at the covariance of those sequences and find these pairs, and they just basically are able to create great databases, covariance database. That's something. But these are things, again, that we had the idea of what the properties should be looking at. They're not creating new things just out of the blue, right? So I think AlphaFold is a great success of engineering, of using all these tools that were available and really pushing all them together. And then being able to show you're able to go the extra step of a problem that people already doing reasonably well. People already being able to do structural prediction of proteins in a reasonably well, not as well as they do. Right? But it's not something that people believed was a completely open, that nobody knew what the problem was.
Yeah, so one overall way to characterize it is if you have a very high dimensional space, machine learning is going to be great. If you have a low dimensional space like superconductors, I mean, I don't know much about superconductors, but I don't think there's that many of them. It's not going to be amenable to these kinds of techniques, right? So high dimensional, complex function spaces, that's where you use it. But if you want to figure out some core principle like DNA, the structure of DNA or something, or what, you know, a Cooper pair, whatever thing is on a superconductor, you know, that kind of principle is a very low dimensional kind of concise entity, and it's not really what machine learning is about.
But that's in science, that's the essential point.
Well, I think there's everything, right? I mean, you have low dimensional spaces and you have high dimensional spaces. So use machine learning for high dimensional spaces, use science and principles for low dimensional spaces.
But it seems that the successes, as we call them, that of the machine learning in some of these contexts at least, are by identifying relatively low dimensional solutions emerging out of those high dimensional spaces. That is, by finding typical structures of folded proteins, discovering those from these high dimensional spaces.
That's because the landscape allows you that, even if you don't find the perfect answer,
Right.
I'm sorry, Daniel.
Oh, that's okay. And I know this is one that always stuck with me. I don't know all the details of this, but the high energy physicists are using machine learning to identify patterns out of these complicated collisions, right? And they don't put in, they don't put in Lorentz invariance into the machine learning process, but it does come out. So when they set it up, the machine learns how to be relativistic. I mean, it does that. So that's a fairly simple first principle that actually emerges from the machine learning when they apply it to try to analyze these patterns by putting in very few basic constraints and letting the machine, the deep networks, go to work on it. So I guess the point is,
I am not sure that they do not put the.
They don't. I've talked to them about it. It just emerges. Yeah. I mean, you might think they'd do better if they could put in some sort of bias towards that to begin with, but they let it just do it, and a Lorentz invariance comes out. It's interesting. But I guess the point is that maybe going back to what you were saying, Randy, that it's approximating high level functional spaces. But if you have too flat of a space, like Jose said, if trying all those different compounds gets you nowhere, Henri, because you're working in that flat space where it's really hard to find the holes, then machine learning isn't going to be much good for you. But if you have a face that has some low dimensional functional representations waiting to be discovered out of a high dimensional space, then maybe it's a useful tool.
Yeah, it'd be interesting just to identify cases where people have been able to go back and really extract the low dimensional sort of story from something that was discovered initially from a machine learning approach. I mean, I think that would be kind of your poster child for like how you could really productively use these things, right? So you master this huge space, you sort of in some sense reduce the dimensionality of this very complex space, and to the point where now a human can go in and look at the principles, so to speak, these low dimensional principles that might explain, X amount of the variance of that solution.
And it should be said also that, I mean, we've like the AlphaFold, we've tried to do some things with proteins where it just, putting two proteins together, it just flat out fails. It doesn't know what to do with them at all. Presumably because it just hasn't been able to learn enough of the space to be able to figure those examples out. So, but yeah, maybe Jose, maybe that's a challenge. Maybe it would be worth writing a sort of retrospective paper pointing out, hey, by the way, great success, and it makes sense that it follows from these, because right now AlphaFold and so on are just running crazy for good reason. But it'd be nice to have a paper like that that sort of looks back at it from a retrospective position.
Their original papers, they actually put all the proper citations, but then after that, you just go to the propaganda papers. So I think they have all the reference to the original Nature paper, but then suddenly you fall into this situation about the miracles. Anyway, we are running over time here. So Piers, what's the...
Yeah, I think this is a natural point to come to an end in this discussion. It's been very interesting. We went at, it's right that Daniel did hijack the discussion. We went very much into the machine learning direction, but it was very entertaining and it was well worth it. I enjoyed it. Thank you.
Yes, maybe the discussion leaders may want to also think about some future ICAM workshop related to this interdisciplinary theme.
I think it's a very nice idea. Yeah. If only machine learning, but also the more general issues of trying to look for new interfaces across the
maybe Daniel, someone has to go back and re-explore the meaning of the word protectorates.
Protectorates, yeah. We could have Protectorate 2.0.
Exactly.
Okay.
20 years of protectorates. Yes.
Okay, so what's the schedule now?
Yeah, so we actually have technically we have a coffee break. And Nikta's talk will start at quarter past 5. Okay. On the West Coast, that is.
All right.
So in 25 minutes. And so we will
to be late.
resume at that point. Yeah.
Okay. See you guys soon. Bye bye.
Great. See you soon. Bye.
I don't know whether I